Greetings of the day. I am Dr. Onika Parmar and I welcome you all in this course Fundamental of Electronic Engineering. Today we are going to discuss about the BJT amplifier and we will discuss the common collector configuration. In today's class we specially focus on the common collector, that is CC configuration, which is also called as emitter follower amplifier circuit. So, these are the outlines for today's lecture. First, we will discuss about the common collector amplifier, advantage of common collector amplifiers, applications of common collector amplifier, small signal voltage gain. We will discuss about the input resistance, output resistance and small signal current gain as well. So, talking about common collector amplifier, this is normally known as CC amplifier. It is a type of bipolar junction transistor amplifier circuit. In the common collector configuration, the transistor's collector terminal is connected to both the input and output circuit. Hence, the term common collector comes in play. This configuration is also known as emitter follower, as the output voltage at the emitter follows the input voltage at the base. Whatever signal we provide at the base terminal is taken as the output from the emitter terminal. Hence, the name comes emitter follower. Understanding the operation of common emitter amplifier is essential. When a small AC signal is applied to the base of the transistor, it modulates the transistor's collector current. The output voltage taken from the emitter closely follows the input voltage, but with greater current capability. This figure shows the emitter follower circuit in the common collector configuration of the amplifier. Here we can see that the transistor is connected with the RE, that is the emitter resistance, and the output is taken from the emitter terminal. The resistance R1 and R2 are the biasing resistance. They are connected parallel to each other. There is a coupling capacitor CC present in the circuit, and the input end, that is Vs, is the source voltage and Rs is the resistance. And we can see that the collector terminal is connected to the VCC supply of the circuit. The emitter is connected to the ground terminal via a resistance Re. So, this circuit forms a emitter follower circuit. Here we can observe the output and the input has a common terminal of the collector node. So, this circuit is known as common collector amplifier. So, as seen in the figure, the output signal is taken off the emitter with respect to the ground, and the collector is connected directly to VCC. Since VCC is at signal ground in AC equivalent circuit, hence the name common collector comes in play. So, talking about the advantages of the common collector amplifier. So, it offers various advantages, and the first one is high input impedance. The common collector amplifier have high input impedance, making them suitable for interfacing with the source that have really high output impedance. So, actually these common collector amplifiers are used in the circuit in connecting between the two circuits. So, this circuit has high input impedance, and there are few circuits which have high output impedance. So, the common collector amplifier are suitable for interfacing with the source that have high impedance. So, high input impedance is one of the advantage of common collector amplifier. Every circuit we design, there are few parameters which a designer seeks, and high input impedance and low output impedance are the two major factors. So, common collector amplifiers provide high input impedance. It also provides low output impedance. They provide a low output impedance, making them capable of driving low impedance load. So, the load whose the impedance are very low. So, these circuits help to drive those low impedance loads. Voltage buffering is another advantage of common collector amplifiers. Common collector amplifier act as voltage buffers, providing unity voltage gain, that is 1, which means that they maintain the same voltage level as the input signal, but with higher current capability. The voltage gain for a common collector amplifier is unity. So, as the signal is provided, the same signal is reflected at the output, but the current capability is now higher. So, they are used in the application which require voltage buffering. They are used in phase relationship. The output voltage is in phase with the input voltage, making the common collector amplifiers useful in the application where phase preservation is critical. So, they have applications where we need to maintain the phase of the circuit. We do not want the output voltage phase to be varied. Hence, where phase relationships are important. Let us discuss about the applications of common collector amplifiers. Common collector amplifiers find application in various electronic circuits because of their very much of advantages. So, the first one is voltage buffering. They are often used to buffer signals between stages of an electronic system. They are used for impedance matching. Common collector amplifiers are employed to match the impedance of a signal source with that of a load. Signal isolation. They provide electrical isolation between the input circuit and the output circuit, which can be useful in preventing feedback. So, they are used where we want to restrict the feedback condition. So, because of the signal isolation, they are used in such circuits. Let us discuss about the small signal voltage gain of the common collector amplifier. Figure 2 shows the small signal equivalent circuit for an emitter follower. So, this is the small signal equivalent of the emitter follower. Let us start from the input terminal, that is Vs. Now, the transistor here in this circuit is replaced with the small signal model and all the external circuitry is same. So, here we can find the input signal Vs passes the resistance Rs and the equivalent parallel resistance of R1 and R2 is connected in parallel to the input voltage. The current IB enters the transistor from the base terminal. Then it goes through the resistance, that is the internal resistance of the transistor, that is R pi. Then here we can find the output is taken from the emitter terminal and the current source has the gain beta IB. and the output is taken across the resistance Re, that is V0. In maximum cases, the coupling capacitor acts as short circuit in the small signal analysis at the same point. So, this is the small signal equivalent circuit of the emitter follower with all signal grounds connected together. So, here it is much easy to analyze. So, starting with the input terminal, that is the Vs, then the current moves to Rs, and that is the input resistance Ri, and the input current is Ii. Then it goes through the equivalent resistance parallel to R1 and R2, or the equivalent of parallel R1 to R2, and it moves in the transistor at the base terminal as the input, and the current here is Ib. Now it passes through the resistance R pi, that is the internal resistance of the device, followed by the current control device. The value here is beta Ib. Then the current I0 flows in the circuit summing Ib and the beta Ib. Then it passes through R0, which is connected parallel to beta Ib current source. Then the output is taken from the emitter resistance, and that is the output resistance of the circuit. So, here we can see in the figure I0 is equals to 1 plus beta Ib. Here Ib is the base current. The output voltage can be written as V0 is equals to Ib 1 plus beta R0 parallel to Re. Writing a KVL equation around the base emitter loop, we get Vin is equals to Ib in bracket R pi plus 1 plus beta into R0 parallel to Re. The resistance Rib is the input resistance looking into the base of the transistor and is given by Rib is equals to Vin upon Ib, that is equals to R pi plus 1 plus beta R0 parallel to Re. We can also write Vin as Vin is equals to Ri upon Ri plus Rs into Vs. Here Ri is equals to R1 parallel to R2 parallel to Rib. Hence Vin can be written as Ri upon Ri plus Rs into Vs. Now the small signal voltage gain is by combining the above equation. As we all know and discussed in the previous lectures, gain is given as output upon input. So, the voltage gain AV is equals to V0 upon Vs, and this value can be written as 1 plus beta R0 parallel to Re upon R pi plus 1 plus beta into R0 parallel to Re into Ri upon Ri plus Rs. So, let us discuss about the input resistance of the common collector amplifier. The input impedance or small signal input resistance of low frequency signal of the emitter follower is determined in the same manner as for the common emitter circuit. The input resistance looking into the base is denoted by Rib and is indicated in the small signal equivalent circuit. The input resistance Rib is given as RIB is equals to R pi plus 1 plus beta R naught parallel to RE. Since the emitter current is 1 plus beta times the base current, the effective impedance in the emitter is multiplied by 1 plus beta. This multiplication by 1 plus beta is called the resistance reflection rule. The input resistance at the base is R pi plus the effective resistance in the emitter multiplied by the factor 1 plus beta. Let us discuss about the output resistance. Initially, to find the output resistance of the emitter follower circuit, we will assume that the input signal source is ideal and Rs is equals to 0. The circuit shown can be used to determine the output resistance looking back in the output terminals. So, here in this figure 4, which shows the small signal equivalent circuit of the emitter follower used to determine the output resistance. So, here we are assuming that the resistance that is at the input will be equals to 0. Now, we will have the ideal source shorted and there will be a resistance that is equivalent to R1 parallel to R2. Then it goes to R pi, then there is a current source that is Gm into V pi. Now, this resistance is connected to Re in parallel and the output is taken from this terminal. Here the current at the output is, we assume it to be Ix and the voltage to be Vx. So, R is equals to V by I. So, Vx upon Ix would be the output resistance. A test voltage Vx is applied to the output terminal and the resulting test current Ix is in the given circuit. So, here the output resistance R naught is given by R naught is equals to Vx upon Ix. Finally, we have got the output resistance in terms of R pi, Re and R naught. R naught is equals to R pi upon 1 plus beta parallel to Re parallel to R naught. In the equation denotes that the output resistance looking back into the output terminal is the effective resistance in the emitter Re parallel to R naught in parallel with the resistance looking back into the emitter. In turn, the resistance looking into the emitter is the total resistance in the base circuit divided by 1 plus beta. This is an important result and is called the inverse resistance reflection rule and is the inverse of the reflection rule looking into the base. So, this is the inverse resistance reflection rule. Now, let us do a numerical on it. So, the numerical is to calculate the input and output resistance of the emitter follower circuit as shown in figure 1. Now, let us assume Rs is equals to 0 and the small signal parameters are R pi is equals to 3.28 kilo ohms, beta is equals to 100 and R naught is equals to 100 kilo ohms. So, here we need to identify the input and output resistance of the circuit. Now, let us work for the input resistance first. So, the input resistance looking into the base is determined as RIB is equals to R pi plus 1 plus beta R naught parallel to RE. So, putting the values of R pi, beta, R naught and RE, that is 3.28 plus 100 plus 1 into 100 parallel to R2. So, we get 201 kilo ohm as the input resistance, and the input resistance seen by the signal source Ri is Ri equals to R1 parallel to R2 parallel to RIB. So, that is 50 parallel to 50 parallel to 201. So, if we find the solution, we will get 2.2 kilo ohm. Output resistance can be determined by the equation R0 is equals to R pi upon 1 plus beta parallel to Re parallel to R0. So, beta is equals to 100. So, our equation becomes 3.28 divided by 101 parallel to 2 parallel to 100, and if we find the value, we will solve it and we will find the value. We will get R0 is equals to 32 ohms. The output resistance is dominated by the first term, that has 1 plus beta in the denominator. So, here we find that the input resistance from the base was 201 kilo ohm, while the output resistance was 32 ohms. So, 201 kilo ohms and 32 ohms. So, we can identify from this numerical that it has high input impedance and low output impedance. So, the term that it has high input impedance and low output resistance is justified from this numerical. Doing the small signal current gain for the emitter follower circuit. So, let us see the figure 5. So, this is the small signal equivalent for the emitter follower circuit. So, here there is a voltage source followed by the input resistance, then the equivalent R1 parallel to R2 is connected, followed by the resistance of the transistor, that is the internal resistance denoted by R pi, then the current source, that is beta IB, followed by the output resistance R0, then there is the biasing resistance for the emitter in parallel, that is Re, and V0 is taken from the emitter terminal. The small signal current gain is defined as AI is equals to IE upon II, where IE and II are the output and input current phasors. Using a current divider equation, we can write the base current in term of the input current as follows. So, IB is equals to R1 parallel to R2 upon R1 parallel to R2 plus RIB into II. Since Gm into V pi is equals to beta IB, then I naught is equals to 1 plus beta IB. So, it can be written as 1 plus beta into R1 parallel to R2 upon R1 parallel to R2 plus RIB into II. So, writing the load current in terms of I naught produces IE, that is the emitter current, that is equals to R naught upon R naught plus RE into I naught. So, we obtain the small signal current gain by combining the equations as the small signal current gain AI is given as IE upon II. We got the value for IE, we got the value for II. Now, we are placing them here and on simplifying we get AI is equals to 1 plus beta into R1 parallel to R2 upon R1 parallel to R2 plus RIB into R0 upon R0 plus RE. So, if we assume that R1 parallel to RB is much greater than RIB and R0 is much greater than RE, then AI is equals to, or the current gain is almost equals to 1 plus beta. Although the small signal voltage gain of the emitter follower is slightly less than 1, the small signal current gain is normally greater than 1. Therefore, the emitter follower circuit produce a small signal power gain. In this lecture, we have discussed about the common collector amplifier. We have discussed about the advantage of common collector amplifiers, applications of the emitter follower circuit, small signal voltage gain of the common collector configuration, its input resistance and output resistance, followed by the small signal current gain. And we have seen that the circuit is called emitter follower because it follows the input from the output, that is, it follows whatever input we have provided in the signal. Here the output voltage is in phase with the input voltage. Its advantage is it has high input impedance and low output resistance. Also, these features makes the common collector amplifier into various applications like the buffering circuit. They are used as a source where the input resistance is very high. So, they have multiple applications in the electronic world. So, this lecture wraps up the amplifier for the BJTs. So, in the previous lecture we have seen the common emitter configuration, and in this lecture we have discussed about the common collector amplifier. So, in the next module we will discuss about MOSFETs. They are one of the very important term in the electronic industry. So, thank you for attending this lecture. See you in the next class.